Good evening students. Today we will start the class with the topic oxidation of alcohols. Basically what happens here, when alcohols are oxidized, first it will give aldehyde, and on further oxidation it will give the carboxylic acid, right? So you can see here, this is the alcohol, and when it is oxidized in presence of chromium trioxide, it gives aldehyde, and then again it undergoes oxidation to give the carboxylic acid. But there is also another way that you can directly yield the carboxylic acid from aldehyde by using KMNO4. Okay, carboxylic acid from alcohol using KMNO4. So let us take an example here. It is the 1 degree or primary alcohol, and by using PCC, which is a better option than KMNO4, you can use the PCC, which stands for pyridine chlorochromate, and you can convert the alcohol directly into aldehyde. Okay, so instead of CrO3, you can also use PCC, which is a better option. Next, the secondary secondary alcohols. What happens, this is the secondary alcohols, right? Because two alkyl groups are attached to the carbon which is directly attached to the functional group, and in presence of chromium trioxide you will get ketone. So here you can see that 1 degree or primary alcohols yield aldehydes, whereas secondary alcohols yield the ketone, and 3 degree or tertiary alcohols do not undergo oxidation. That should be remembered. Now, there are three sets of reactions in which copper is used. So, when tertiary alcohol vapors are passed over copper at a temperature of 573 Kelvin, you will obtain an alkene, and the number of carbon atoms present in the alkene is similar to the number of carbon atoms in the alcohol. So, when you will use a tertiary alcohol, you will get an alcohol whose carbon number is similar, and the name of this alcohol is what? It is 2-methyl propene, right? Because 1 2 3 carbon is there in the parent chain, and this is the alkyl that is a methyl group. Okay, alkyl group, that is methyl, and it is present in carbon number 2 according to the double bond that we have to follow. So this is 1, this is 2, and this is 3. So it is 2-methyl propene. Next, when we use secondary alcohol, when we pass the vapors of secondary alcohols over copper at a temperature of 573 Kelvin, we will obtain a ketone. So you can see that basically during oxidation, what happens, the secondary alcohols tend to form ketones, primary alcohols form aldehydes, and whenever we use like chromium trioxide, the tertiary alcohols do not produce any yield. Okay, and but if we use copper, then what happens, then alkene is produced. So this thing you have to keep in your mind. Then for primary alcohols, we will obtain an aldehyde. So this thing you have to fix it. When we oxidize an alcohol, we will get aldehyde, and again when we will further oxidize it, the aldehyde, we will get an carboxylic acid. And the formation of aldehyde or ketone, it depends on the type of alcohols, whether primary or whether secondary. Next, this is a different topic. So our alcoholic portion is over. We have done the preparation, we have done the properties, we have studied about these reactions. So whatever reactions we have done till now for alcohols is important. So next we are going to do the reactions of phenols. Preparation of phenol is already done. After reaction of phenols, we are going to study preparation of ethers and reactions of ethers. Okay, so let us see the reactions of phenols. So instead of like writing every point one by one, so it is better you make a chart for organic chemistry, so that it is all the important things or all the reactions of one compound is just in front of your eyes, so that you can compare and you don't get confused between different types of reactions that you are going to get. So this is a chart that I have prepared, in which we are going to study the reaction of phenols, and we have placed the phenol molecule here. Okay, so we are going to study about nitration, about halogenation. Okay, so let us see the first reaction here. When phenol is reacted with dilute nitric acid, remember in chemistry it is very important to be very particular for the chemicals that we are using. A difference in temperature can make a difference in the product. A difference in the proportion of the acid and ratio of acid to water can make a vast difference in the production. So here you have to be very clear, and as you can see we have got two reactions here, that is the dilute nitric acid and concentrated nitric acid. So both these acids will give us different products, so you have to be very particular, you have to be very conscious about the temperature, about the pressure. A little difference can make a vast difference, so that's what we are going to say. Now when dilute nitric acid is used you will get orthonitrophenol and paranitrophenol. Okay, so this is the product, these are the products that you can get. Now when after obtaining the products, we are going to study in details, but let me say this, the summary. So after using dilute nitric acid you will get orthonitrophenol and paranitrophenol, that is the case. Now since you have got two products here, now if you want to obtain the, or if you want to abstract the orthonitrophenol or say the paranitrophenol, then how you can do it? This can be done by simple steaming. Okay, you can separate them very easily, there is not a slight problem in separating them. Now why we use the orthonitrophenol and paranitrophenol? Now again you have to remember here one thing. In case of resonance, when you draw the structure for resonance of phenol, what you can see that the electrons are rotating around the benzene ring, right? So when you draw these structures, you can observe that the negative or the electron density is present either here or at the para position. This is the ortho position, this is the meta position, and this is the para position. So whenever you will draw the resonance structure, one thing you will observe that the electrons that are present here will be pushed towards this carbon. So here one negative will be present, again this negative will be pushed towards the bond and it will make a double bond. Again this double bond will be pushed here and one negative sign will be obtained. So the negative signs or the electron density are obtained at the ortho position and the para position, but in the meta position no such electron density is accumulated. So since you're talking about the electrophilic substitution, means NO2 is an electrophile, an electron deficient species, you can say in short. So this electron deficient species will always find attraction towards electron rich species, means positive attracts the negative. Okay, so that is the case here. Let us see in details. Now in phenol reactions, we are going to mainly study about the electrophilic aromatic substitution. Okay, electrophilic aromatic substitution means what? The electrophiles or the electron less or electron deficient species will substitute an atom in the aromatic ring or the benzene ring. So the first point is that reactions that take place in the aromatic ring. So this in the aromatic ring only the reaction is going to occur and OH is not going to change. Okay, so this thing you have to keep in mind. Next, resonance effect caused by OH group makes an ortho and para position electron rich. So here one question may arise that why the nitration occurs in the ortho and para position. So that may be the question, why electrophiles attract the ortho and the para position. The answer is you have to draw the resonance structure. Okay, if you draw the resonance structure, you can observe that where are the negative signs, where the electrons are accumulating. First at this position, second at this position, third at this position. So this position is known as the ortho position. This and this is known as the meta position, and opposite to the OH is the para position. So you can observe that in the ortho and para position only you are getting the negative sign. So at that point only, at those points only, the electrophiles will find attraction. Clear? So these are the points that you have to remember, and this is a very important question. Actually, it comes for 1 mark sometime, that why ortho and para positions are more active during electrophilic aromatic substitution, or why the meta position is not active during electrophilic aromatic substitution. The answer is due to resonance. And elaborately you can write you can draw the structure of resonance and give the cause that is written here, that resonance effect caused by OH makes ortho and para position electron rich, while no such observation is made in the meta position. So this is the reason. And if you are confused about ortho, meta and para, this is the point that I have written, and I know you are not confused because till now you know which are the positions. So if this is the substituted group, then relative to this group, this is the ortho, this is the meta, this is the para. Again the cyclic structure, this is the meta and this is the ortho position. So this is now very clear that nitration, in nitration reaction, NO2 group is introduced in the phenolic part. So when we use dilute nitric acid, we are going to get two products, that is your orthonitrophenol and paranitrophenol. Since meta does not work here, so this thing you have to keep in mind. And for concentrated nitric acid, no water is present, then you will get the nitro group in all the positions of ortho and para. So there are two positions of ortho and one position of para, as you can see there. This is the group. So this compound is actually picric acid, and in IUPAC name you will get 2,4,6 trinitrophenol. So this is the compound. So here you have to be very observative about what acid that you are using, whether in the question dilute is given or concentrated is given. So if concentrated is given, one compound is produced. In dilute, two compounds will be produced. Next, halogenation, where we are going to introduce the bromine in the compound in phenol in presence of CS2 and a temperature is 273 Kelvin. So again the same thing here repeated. Nitration, in case of nitration we have used NO2. Now in case of halogenation we are going to use Br if we are taking bromine. So this is the minor product and this is the major product. More amount of product will be formed for this. So here also you will get again ortho, this is ortho bromophenol and this is para bromophenol. Next, if we use bromine water along with the presence of bromine, here you are going to use 3 Br2 and here only 1 Br2. Next, you are going to get only one compound here, that is 2,4,6 tribromophenol. So there is a similarity between the concept of nitration and halogenation, but obviously the reagents will be different and the compounds will be different, but you can see that you can relate it little bit. And if you can remember, if you can make the relation between nitration and this halogenation, then it is very easy to remember the products. There is not much problem. Next, let us use sodium chromate, sodium dichromate in presence of sulfuric acid. You will get benzoquinone. Remember we are doing reactions of phenol plus sodium dichromate and sulfuric acid. You will get benzoquinone. Two oxygen will be introduced in the benzene ring along with the double bond. Next, another reaction is that if you use zinc in presence of phenol, you will get benzene plus ZNO, zinc oxide. So these are the reactions of phenols which are very easy. Next we are going to study two name reactions, two very important reactions, and in the examination they usually come as short notes, or like 2 or 3 marks it will come mainly for the reactions.